So here's a question. How do harmonic currents really add up to make up the distorted waveform? And we've talked about calculating THD, but how does that all work? So in order to calculate THD and add up all the waveforms together to make up harmonics and make up these waveforms, it's actually, you have to go back to the basic principle that harmonics don't really exist. It's just a mathematical representation of a waveform. So let's take a look at a couple waveforms and analyze them backwards to make sense out of what that really means. So if we take a look at this waveform and we take one electrical cycle out of that waveform, we can do a fast Fourier analysis or a Fourier analysis on that waveform and come up with the appropriate levels of different frequencies. Like, for example, the fundamental, in this case 100%, the third harmonic 20%, and fifth and seventh, and so forth. So in calculating total harmonic distortion, we add up the sum of the squares of all those different harmonics, and we come up with, in this case, 23.8%. However, that's just the reverse of what the calculators and the computers are doing to give us the numbers. But really, when we add those up, we have to look at it a little bit more specifically as to how they break down those waveforms. So now, if you look at this waveform, this is actually a 6-pulse drive waveform, and we would expect 5th and 7th and 11th and 13th and so on. So what I want you to look at, though, is if we add up with all the exact right mathematical representation with the correct phase angles, we get that waveform. If we take the exact same information in terms of magnitude of each, and going back to that previous wave analysis where we just took the magnitude of each harmonic and added up, we're going to get a different waveform if we use a different phase angle. So what does that mean? In this case, we use all phase angles of 0. So let's just look at one harmonic, just the fifth harmonic. This fifth harmonic is, in this case, at about 90 degrees when the fundamental is close to 0 here. And in fact, this fundamental current is not even referenced at 0 either. This is referenced to the phase A voltage. So each meter, and when you're analyzing systems, they take one of the voltages and say, okay, this is our reference. So voltage phase A is at 0. When voltage phase A is at 0, this one is actually about 13 degrees behind, so it's a lagging current. The fifth harmonic is at about 90 degrees with reference to that phase A voltage. And then if you look over here, if we put both of them at 0 degrees, again, adding that together and all the other harmonics gives us a totally different wave shape, which is kind of interesting. And again, all mathematically related. So why is that important? If we add up all the harmonics, we end up with a THD. But if we add up the actual amount of current flowing on the system, we want to really analyze the system to make sure that we have enough current capacity to withstand everything that we're going to use on that system. And a lot of people get concerned about, for example, 20% distortion. But if we have 20% distortion on a power system, if we have 20% distortion, we really only have about 102% actual RMS current. So if you designed your system to work at 100%, but it fails at 102%, it might be a little marginal. All of this comes into play when you analyze the waveform, trying to make sense out of how those harmonics add up on the power system.